Pressure loss in bends. Why turning flow costs energy. Curved flow inside a pump. A centrifugal pump is full of curved flow passages. The liquid enters through the suction side, reaches the impeller, and then continuously changes direction as it moves through the curved blade passages. The flow also changes direction through the casing and, outside the pump, through bends in the connected piping. So curved flow is everywhere in a pump system. But every time we force the liquid to turn, there is an important engineering question. What does that turn actually cost us? What does the turn cost? At first, it may seem that changing the direction of the flow should not create much of a problem. The liquid enters the bend, follows the curved wall, and leaves in another direction. But real fluid does not move through the bend perfectly. The curvature changes the pressure distribution and the velocity distribution inside the passage. And those changes can create additional hydraulic loss. So let's first understand what actually makes the fluid turn. Pressure across the bend. When fluid moves through a curved path, it needs an inward force to continuously change its direction. That force is provided by a pressure difference across the passage. The pressure becomes relatively higher near the outer wall of the bend and lower near the inner wall. This pressure difference pushes the fluid toward the center of curvature and allows the flow to follow the bend. So the pressure difference is necessary for turning the fluid. Pressure gradient is not the loss. But this is a very important distinction. The pressure gradient required to turn the fluid is not, by itself, the hydraulic loss. Static pressure can increase in one region and decrease in another without useful mechanical energy necessarily being destroyed. The actual irreversible loss comes from the way a real fluid responds to the curved passage. Viscosity, velocity gradients, secondary motion, wall shear, mixing, and sometimes flow separation are what create the additional loss. Keep this distinction in mind throughout the video. Flow through the curved passage. Now imagine water entering this curved channel. At the inlet, most of the fluid motion is directed along the passage. As the water enters the bend, every streamline has to gradually change direction and follow the curved geometry. The fluid continues from the inlet, around the turn, and toward the outlet. But the important point is that all the fluid particles are not moving at exactly the same speed. That makes the real flow much more complicated than this simple picture. Real velocity profile. If the velocity were perfectly uniform across the passage, every fluid particle would respond to the bend in approximately the same way. But real flow has a velocity profile. Because of viscosity and the no-slip condition, the fluid very close to the wall moves more slowly. Moving away from the wall, the velocity becomes higher. So the central part of the flow carries more momentum than the slower fluid near the walls. And once this non-uniform velocity profile enters a curved passage, an additional flow motion begins to develop. Primary flow. First, we have the primary flow. This is the main motion carrying the fluid through the passage from inlet to outlet. If we look at the duct in cross-section, this main flow is traveling downstream, into the page. The velocity is normally highest away from the walls and lower near the walls. But in a curved passage, the fluid also begins moving across this cross-section. Secondary flow. The faster-moving fluid near the core has greater momentum as it travels around the bend. The slower fluid near the walls responds differently. Because of this difference, the pressure distribution across the bend does not balance every part of the velocity profile in exactly the same way. An additional circulation develops across the passage. This is called secondary flow. Instead of the liquid moving only downstream, part of the flow also circulates across the channel. In a simple curved duct, this can appear as a pair of counter-rotating secondary flow cells. The primary flow is still carrying the liquid downstream, but this additional cross-passage motion is now superimposed on it. Why secondary flow costs energy? And this secondary motion has a cost. The fluid now follows a more complicated three-dimensional path. Additional velocity gradients are created. Wall shear increases. Different regions of fluid are transported across the passage and mixed together. All of this gradually converts useful mechanical energy into irreversible fluid losses.
So the sequence is
Secondary motion, stronger velocity gradients, more shear and mixing, and finally additional hydraulic loss. This is why a curved passage can create more resistance than an equivalent straight passage. Attached flow. But secondary flow is not the only possible source of loss. Imagine a bend where the streamlines are still able to follow the walls smoothly. The flow remains attached. There may still be secondary motion and additional resistance, but the fluid is generally following the intended passage. Now, let's make the turn more severe. Separation starts. Near the wall, the fluid has already lost momentum because of viscosity. If that low momentum fluid encounters an unfavorable pressure change and the geometry forces it through a sharp turn, it may no longer have enough momentum to stay attached to the surface. The streamline begins to lift away from the wall. This is the beginning of flow separation. Recirculation. Once the flow separates, a recirculation region can develop behind the separation point. Inside this region, part of the fluid may move backward locally, while the main flow continues toward the outlet. This separated region creates strong mixing between the recirculating fluid and the main flow. That mixing produces additional irreversible loss. So a sharp bend does not create more loss simply because the fluid turns through a larger visual angle. The problem is how strongly the geometry disturbs the real flow. Head loss equation. Engineers normally represent this additional fitting loss using a simple head loss relationship. The head loss, HL, is equal to K multiplied by V squared over 2G. Here, HL represents the hydraulic head lost through the fitting. K is the loss coefficient associated with the geometry and the flow condition.
And
V is the representative average velocity. We don't need to calculate a particular K value in this video. The important physical message is this: the geometry matters and velocity matters strongly. Because velocity appears squared in the relationship, increasing velocity can increase the loss very quickly. So pushing more flow through the same bend can make that bend hydraulically much more expensive. Large radius versus tight radius. Now compare these two bends. Both are changing the direction of the flow, but the first one uses a larger, smoother radius. The second forces the liquid through a much tighter turn. In the smoother bend, the fluid has more distance to change direction gradually. In the tighter bend, the velocity distribution becomes more strongly distorted, secondary motion can become stronger, and the risk of separation can increase. So, in general, a smooth gradual turn is hydraulically better than an unnecessarily tight turn. The same turning angle does not necessarily mean the same loss. The geometry of the turn matters. Connection to the impeller. Now return to the centrifugal pump impeller. An impeller passage is obviously much more complex than a stationary pipe elbow. The passage is rotating. The blades are curved. The flow area changes continuously, and the flow is three-dimensional. So we should never treat the simple pipe bend equation as a complete model of flow through an impeller. But the underlying engineering lesson is still extremely useful. The fluid should be guided through the blade passage as smoothly as practical. Poor curvature or abrupt geometric changes can create stronger flow distortion, unwanted secondary motion, separation, and additional hydraulic loss. That is one reason smooth blade curvature and controlled passage geometry are important in pump hydraulic design. Piping and plant connection. The same principle also matters outside the pump. A real piping system can contain many elbows and fittings. Each one adds local hydraulic resistance. That means the pump must overcome both the friction losses along the straight pipe and the additional local losses created by bends, valves, expansions, contractions, and other fittings. But a suction side bend can create another problem as well. If an elbow is located too close to the pump inlet or creates a strongly distorted flow condition, the pump may receive a non-uniform velocity profile or unwanted swirl. So the piping geometry can influence both how much head the system requires
and
the quality of the flow delivered to the pump. Guide the flow. So when we look at any curved hydraulic passage, the design question should not simply be, can the fluid make the turn? Of course, the fluid can be forced around many different shapes. The better engineering question is, can we guide the fluid through the turn smoothly? Good geometry gives the flow enough space to change direction gradually. Poor geometry forces the liquid through abrupt changes and creates stronger distortion. So think of the difference as guide the flow versus force the flow. Both may achieve the same change in direction, but the hydraulic performance can be very different. Interview question. Now, let's convert this into a useful interview question. Why is the pressure or head loss through a pipe bend greater than through an equivalent straight pipe? A weak answer would simply be, because the fluid changes direction. That does not explain the actual mechanism. A better answer is, curvature produces a non-uniform pressure and velocity field and creates secondary flow. This additional motion increases velocity gradients, wall shear, and mixing. And if the bend geometry is severe enough, flow separation and recirculation can create even more loss. That is the engineering reason. Takeaway 1. Let's finish with 3 important points. Number 1. A pressure gradient is required to turn the flow. The higher static pressure near the outer side of the bend and lower pressure near the inner side provide the inward force needed for curved motion. That pressure gradient itself should not automatically be confused with hydraulic loss. Takeaway 2. Number 2. The irreversible loss comes from real fluid effects. Secondary flow, increased velocity gradients, wall shear, mixing, and possible separation all contribute to additional hydraulic resistance. Takeaway 3. And number 3. Smoother turning generally reduces unnecessary hydraulic loss. The objective is not simply to make the fluid change direction. The objective is to guide the flow through that change of direction with as little unnecessary disturbance as possible. Remove the bend. But now consider something interesting. Everything we have discussed in this video involved a curved passage. So let's remove the bend completely. Imagine the same liquid moving through a perfectly straight passage. There is no curvature, there is no turning, and there is no curved channel secondary flow. But the fluid still loses energy as it travels downstream.
why?
Because the wall is continuously interacting with the moving fluid. The liquid at the wall is slowed by viscosity, and shear is transmitted through the fluid. So even a perfectly straight passage has an unavoidable hydraulic loss. Next video. And that gives us the next engineering question. Where does the energy go when fluid simply moves along a wall? That takes us directly to skin friction and friction losses. In the next lesson, we'll connect the boundary layer, wall shear, surface condition, and hydraulic energy loss into one simple physical picture.